Welcome back, everyone. In this lecture, we're going to go through solutions for the project exercise with dbScan. Let's get started. Okay, here we are at the project exercise notebook. Now, as you may have been able to tell, this project, especially clustering projects in general, are a little more open-ended. And with this particular project, we really just had two main things we wanted to do, which was to discover clusters within this unlabeled data set, as well as identify any outliers and what the features are that are pushing them to be outliers. So if we come back down here, what we can do is begin by running these few cells and then identifying what we actually have in our data set. So we have these values for spending on different categories and then the channel or region that they actually were spent on. And we can see it's a relatively small data set, only 440 entries, and we can see pretty much nothing is missing, so we don't need to worry about missing data. We'll move on to EDA, which is pretty simple. The first one, I wanted to create a scatter plot. So we will call SNS scatter plot, set the data equal to df, and then we simply set the column names that we're looking to discover. So that's milk, and then y is grocery. And then it asks us to make the hue the channel. So if we just run this, what can we glean from this? Well, we can see that for channel 1 users, their spending on grocery and milk is typically a lot less than the channel 2 users that are a darker color. So if you're in channel 2, you're very likely to spend more than in channel 1. Next, we wanted to use Seaborn to create a histogram of milk spending. And if also, could you figure out how to use Seaborn to stack the channels instead of having them overlap? So I'll show you both versions of that. If we say hist plot from Seaborn, pass in data as df, x is the milk, it's the continuous spending column, and then we'll say hue is equal to channel. If you just run that, then you'll pretty much see one histogram behind another. They're not technically stacked in the sense that they're stacked vertically. They're kind of stacked on the z-axis going into the screen, if you will, where you can see one histogram here for channel 2, and then behind it you see channel 1, and depending on the palette, this is sometimes hard to tell. So what we can also do is set something like palette equal to something very distinct like set1, and try to make the color difference even more clear. But what we can also do is to make them truly stacked on top of each other. For example, this little bar, instead of being kind of on top z-axis wise into the screen of this long red bar, we want this little chunk of blue to be on the bottom or on the top of this. So we can say is multiple equals to the string stack. You can check this out easily on the Seaborn documentation, has an example there. You run that, and now you can see these are actually being stacked on top of each other, which should give you an idea of how they relate. And again, we can see here that channel 1 distribution of milk seems to be much lower than the channel 2. So channel 2 definitely have higher spending for the majority of it, even though there's less of a count of actual people in channel 2. After that, we wanted to create an annotated cluster map of the correlations between spending on the different categories. So how do we actually do this? Well, for one thing, we have to get rid of everything that's not a category. So note here, we're only looking at milk, grocery, detergent paper, delicatessen, fresh, frozen. We're not looking at channel or region, which means when we actually call cluster map, we should be passing in our data without the region and channel. So we'll say drop region column and drop the channel column, and then say axis is equal to 1. And then remember, we're interested in the correlation here, and we also want the annotation to be true. So when you run that, what's happening here is we're getting our data frame, we're dropping the region and channel along axis equal to 1. That gives us only those spending categories, milk, grocery, etc. Then we figure out the correlation between them, and then we say annotation true, so we can see the actual correlation values and how they're clustered together. So what are we actually discovering here? It looks like there's kind of higher correlations between grocery and detergent papers. Over here, that seems to be what's happening. Actually, this is incorrect. It's higher between grocery and milk, excuse me. So we see 0.73 very highly correlated between milk and grocery. And if you see right here, milk and grocery are also being clustered together. So kind of the overall arching clusters, you can see them here, milk, grocery. Sometimes what you want to do, if it's just a correlation matrix, it doesn't really make sense to have repeated hierarchies here, because notice, this is essentially a duplicate across the diagonal. So probably what you want to do is, if you recall from cluster map, if we expand on this, you can say for row cluster or column cluster to be false. And because we're essentially duplicating clusters, it might be a good idea to just add that in for one of these to be false, because the hierarchies are going to be exactly the same because they're essentially the same along the diagonal. And here we can get a better idea of what's actually being clustered together. Again, milk and grocery being clustered together along with detergent papers versus delicatessen, fresh, and frozen. Okay, so we're going to move along here. And lastly, we want to create a pair plot of the data frame colored by region. This one's super simple. Obviously, you want to be careful for really large data sets of running this, but we can say pair plot, pass in your data frame, hue is equal to region, and then for this sort of thing, I really like the set one palette. It just makes it clear to my eyes. And you can play around with your palette choice when it comes to the color maps in Matplotlib. The defaults will be something like magma colors. Okay, so there's our pair plot. We can see the relationships between the different spending categories. Typically, it looks like as you spend more in one category, you're typically spending more in another. But for certain things, the distribution is quite tight. So delicatessen seems like nobody spends too much on it. There are certain outliers here in certain regions. So do we actually see a main difference between the regions? I cannot see it myself. Granted, there are a lot of points stacked on top of each other. You could begin honing in on a particular scatter plot, adding in an alpha to see where the points are lying on top of each other. But for the most part, just based off region alone, I don't see any major difference. Unlike channel, which you recall if we set hue to channel and run that, you should begin to see a difference in the actual amount of spending. Because recall, up here when we were running these scatter plots, we saw a major difference between channel. It looks like channel 2 tends to spend more, and we saw that as well from the histogram. So if we do this for a pair plot, now you can see definitely a distinct difference, especially on some of these categories, of spending between channel 1 and channel 2. So something to keep in mind here, it looks like channel is way more important than region as far as being a distinct qualifier of how much someone is spending. So now let's move on to the dbScan portion where we're trying to discover clusters and outliers. And because the values of the features are in different orders of magnitude, it's not a bad idea to scale data. Something I'm often asked is, when do we actually scale data? Which algorithms should I scale for? If you're ever in doubt, think of two things. One, is there some sort of distance metric being used? If so, probably a good idea to scale. And number two, if you really don't know, just go ahead and scale, as it probably won't affect the algorithm poorly. It's only due to enhanced performance if it was necessary. So whenever you're in doubt, just go ahead and scale, but usually also a quick Google search will usually answer the question of whether or not it's appropriate to scale or if you need to scale. So we can say import standard scalar here or min-max scalar, create an instance of that scalar, so we'll say standard scalar, run that, and then let's create a scaled version of our X features. So we'll say scalar fit transform. Something to note here is we didn't really bother changing region or channel into dummy variables, and that's because there really weren't that many channels to begin with. So treating channel as 1 and 2 is not going to have a major effect from treating channel as a single column of 0 or 1. And same for regions. If we recall regions here, if you take a look at it, it's really just 3 distinct region types. So region 1, 2, and 3, and then channel 1 and 2. Not a huge deal for the case of dbScan clustering to create those as dummy features. Obviously, you could do that if you really wanted to. It wouldn't affect it either way. So we're going to run scaled. So notice I passed in my data frame, all features, nothing was missing. So I scaled with fit transform. Now if I take a look at my scaled X data, it is this scaled array. Okay, so I have that ready to go. Now let's use dbScan to create that for loop. Pretty much the exact same thing we showed in the lecture. So how do we do that? We're going to say from scikit-learn.cluster and import dbScan. And then let's keep track of the outlier percentage. You could also keep track of the number of outliers themselves, but in this case, we only asked you to keep track of the percent of outliers in order to build out that plot later on. We'll say for epsilon value in NP linspace. You could have chosen any spacing you wanted, but we'll match what we said it was in the solutions, which is 0.001. Go to epsilon value of 3 and give me 50 points. More points you choose, the longer it's going to take to run this. We'll say dbScan is equal to dbScan, and I'm going to say epsilon is equal to epsilon. And recall, for minimum number of samples, we asked you to have it be equal to 2 times the number of features, which is pretty much a good starting point if you're unsure what to set it to. So we'll say minimum samples is equal to 2 times scaled X shape 1. That's essentially the number of features because it's the number of columns in scaled x. And I believe we capitalized scaled x, so let me leave that there. Okay, then we're going to say dbScan, and I'm going to fit it to my scaled x. And then I'm going to log the percentages that are outliers. So recall the way we calculate that. So I say %outliers is equal to 100 times, and then I'm going to say the NP sum of dbScan labels underscore, where it was equal to -1. And then once I have that, I'm going to divide it by the total length of the number of labels underscore. So what I'm doing here is I'm just counting how many labels were equal to -1, that is outliers, and then what percentage of that was it out of the total labels. Then we'll say outlier %, and I'm going to append this new %outliers. So go ahead and run that. Should be relatively quick for this small data set. Then we're going to create a line plot. Let's go ahead and click that out. So we're going to say SNS line plot. X is equal to, should be the same spacing we chose above here. So we're going to say linspace right here. And then we're going to say Y is equal to the outlier %. And then we're just going to go ahead and run this. And you should see this behavior. Now keep in mind, what are we looking for here? The y-axis is the % of points as outliers. Obviously, we don't want to have everything be an outlier. It's kind of useless to just classify everything as an outlier and then leave. That doesn't tell us any information. But it's also kind of in the same pattern to say it's useless if absolutely nothing gets classified as an outlier, especially after we saw the behavior of some of these. Like some of these points should definitely be outliers. So where does this come into play as to choosing a reasonable epsilon value? What you would need to do is do a little bit of visualization, talk to someone that has domain experience and say, hey, what percentage of points should I be expecting to be outliers here? I see quite a few, and where do I want to have the cutoff? Do I only want to have, for instance, these 5 particular points be outliers and everything else is pretty much on trend? Or maybe I'm trying to do something like overall, maybe these 20 points should be outliers that are kind of out there and not within this cluster. Or you can just let dbScan sort of kind of guide you as you take a look at this plot right here. So what are we looking for? We're really looking for this inflection point where it begins to level off. We can make an argument that it's leveling off at somewhere between 2 and 3 epsilon. Let's go ahead and run it with 2. So we'll choose epsilon, which means we should probably retrain our model with just having epsilon equal to 2. So we'll say dbScan epsilon equal to 2, and we can also set minimum number of samples equal to scaled x shape of 1. Go ahead and run that. And once we have that epsilon value chosen and that model run, we want to go ahead and fit it. So we'll say dbScan, go ahead and fit this to our scaled x values. And we're going to create a scatter plot of milk versus grocery, but now I'm going to color it by the labels that were discovered upon this fitting. So recall, once I've actually performed the fitting, I can say dbScan labels and see these actual labels in order to color it for hue. So we're going to say SNS.scatterplot. And then what I'm going to do here is say my data is equal to my original data frame. X is equal to milk again, or actually to grocery. Y is equal to milk. Sure, it's on the same line. Y is equal to milk here. And then I'm going to say hue is equal to not anything from the actual data frame, but instead to dbScan labels. If you want to make this easier, you could also just, and later on we do this, add labels as a new column in data frame. But you can pass in a raw array like this as well. So we run this and we see this behavior. So what is this telling us? It looks like some of these are outliers in possibly other spending categories that we couldn't quite tell just from looking at grocery and milk. Obviously we see these points that are clear outliers even to the human eye, but if you look carefully, there are some points here as well that are definitely closer to what is kind of typical spending, but this dbScan is still saying there are outliers, because recall dbScan can look at all the features at kind of the same time, so to speak, while we as humans are kind of limited to 2 or 3 features max depending on how we're actually visualizing this. So something else you can do just to make it clear depending on your screen is sometimes you may want to set this to a non-default color palette to really see those points pop out. So I really like set 1 when it comes to visualizing the outliers because they pretty much default to -1, which is bright red. So I can see here these 2 points, kind of the interesting ones of what's causing them to be outliers versus these blue points way out here are still not outliers according to dbScan. So maybe you want to actually explore this based off of different columns as well. So you can copy this, paste it here, and start changing up. Maybe you want to see X label as detergent papers, so you can copy that. So we ask you to do another scatter plot to begin to discover this as well. And here you can kind of see the same idea. Obviously these points, outliers, but also notice once you go beyond a certain threshold of milk spending, you're an outlier. And we can see some kind of hidden red point here where maybe reasonable association with milk and detergent papers. So it's probably a point that's spending way more in some other category that we're having trouble visualizing all at once because we're limited to 2 or 3 dimensions just as human beings. So what we should do is create a new column of the original data frame called labels. And the reason for that is there's only a certain point that visualization can take you to. After that, you probably want to look at just numbers all at once. So we can do that by saying df and then say labels is equal to dbScan labels underscore. Take a look at the data frame, and we can see now we have this labels. And the reason this works is because we didn't do any sort of train test split. The dbScan labels are connected by the index position, so we can easily just do this assignment. That's not always going to be the case in terms of train test split. We're going to have to match them up to training labels to training sets or test sets to the original test data frames. Here, because everything was set the same, there was no train test because it was unsupervised, we can just directly match it like that. Okay, so we have this new labels column all the way at the end. What can we do with this? There's a lot we can do with this. Something that would be interesting to do is compare the statistical mean of the clusters and outliers for the spending amounts on the categories. So we want to do something like this. Clearly, you can see that the index has been changed to labels, so that should be telling your brain to do a group by. So what we're going to do is take df, and I'm only interested in the actual categories. So I'm going to, again, drop the channel and region along axis is equal to 1. And I'm going to set that only for categories, since that's kind of what I'm interested here. And then I'm going to say category means is equal to these categories grouped by the new label column we just created, and then calculate the mean values. So run that, and whoops, make sure we set this correct. I believe it's labels. There we go. Cat means, and we get this. So right off the bat, what are we looking at here? Maybe you want to just pass this straight into an SNS heat map in order to colorize it. So we can say SNS heat map, cat means, and then say annotate this equal to true. And what's nice about this, it's essentially going to show you the exact same data frame, but now it's going to have it colored. And recall, you can always do something like PLT, figure, fig size to make it larger. Maybe you want something like 10:6 and higher DPI, just so you can get a better idea of what's happening here. So what looks to be the main differences here? Just based off these numbers, we can see that for the case of going from dark to light, light is when you're spending a lot of money or a lot on a particular category. So clearly outliers are defined by these vast spending amounts that are way higher than what we see here for labels 0 and 1. And it looks like there was 3 categories that were really pushing this, and it was fresh, milk, and grocery. So that's really difficult to visualize 3 dimensions. You could do it, but when it comes to 3 dimensions, adding then 3 clusters and coloring everything, that's hard to tell. It's easier to see this in a colorized heat map of the data frame. So one of the main conclusions you can see here is the true outliers, and what's really pushing something to be an outlier looks like just overall spending amount. And clearly it looks like spending a lot more on things like fresh, milk, and grocery. And we can see it's a whole order of magnitude. This is 10 or times 10 to the power 4. These other ones were just still times 10 to the power of 3. You can see it's actually really distinct in delicatessens as well, where we see here 7.4 times 10 to the power 3, where these are much darker as well. So essentially, we're just spending a lot more money on certain categories, and across the board, you're really spending a lot more. You can see here, pretty much the top row is lighter on everything. And what you can do is, if you just want to now begin to understand the distinction between labels 0 and 1, is to do something like this, where you say cat means and say LOC, and we're only now interested in the 0 and 1 rows. And this will show you now just comparing labels 0 and 1. You'll have to keep in mind, now this is in the context of just one cluster to another cluster, not the entire data set. So this color scale kind of is only meaningful in terms of comparing one cluster to the other. So now this helps you decide, well, what is the differences between the two clusters? And again, it's going to be spending amounts. Some things are spending way more on. For example, cluster 0 spends a lot more on fresh and milk, and they spend a lot less on things like grocery and frozen. And then maybe roughly the same on detergent papers and delicatessen. And then something else we mentioned is maybe you want to scale this using min-max scalar. That's pretty much the rest of this, is to do the exact same thing, except do a min-max scalar. The way you could do that is just say, and we're kind of doing all the last tasks together here because we're explaining them and processing them along the way. You can say import min-max scalar. Whoops, make sure we spell that right. Import min-max scalar, create a scalar. So say scalar is equal to an instance of min-max scalar. Say data is equal to scalar fit transform. And you can actually fit transform the cat means that we created above or below this. So typically you probably want to put this below and have everything in order. So I'm going to run this here and scale it here. So we'll say this is my scaled cat data or cat means data. And then what we're going to say here is scaled cat data. Right now, it's just an array. And notice here the outliers are the top spenders in everything. So this is kind of a really easy way to see that, so you don't have to compare raw numbers. But in order to do this a little easier, we can say PD data frame, scaled cat data, and that's our actual data, and then pass in the index from cat means, and pass in the columns from cat means as index and columns. So recall for data frame, it goes data, index, columns. So all I'm saying here is pass in the scaled version of data, but keep the original index and column names. So we can go ahead and run that. And now we have this nice data frame, everything's scaled. And so this right away tells you the outliers are the highest spender in every single category. And what's also interesting is it immediately tells you cluster 1 is the lowest spender in milk and grocery, as well as detergents and delicatessen. It's kind of just a more extreme way of having your eyeball go to what are the main differences here. And then again, you can also do heat map on this to clarify those points further just with color. Now, sometimes this isn't super useful because you can see this top row is essentially all 1. But what's telling you? Well, it's just saying, hey, outliers, they're pretty much defined by being the top spender in every single category. Now, we saw previously when we were looking at raw numbers, in certain categories, they're not an extreme amount higher. But here we can see when we scale them, they are pretty much the highest. And we can see then the lowest categories as well. So this is all that we were talking about here. Again, we create another heat map with the outliers removed. You can do this without the outliers. Same idea, just grab labels 0 and 1, do the comparisons. So what spending category were the two clusters most different in? And we can see here it was detergent papers and milk, but obviously they're pretty much different in all the categories to some degree. All right, that's it for the project. Hope you enjoyed it. Feel free to explore the data set further. I'll see you at the next lecture.